Hey y'all, this is a thermodynamics skill chunk on heat engines and the idea of second law efficiency, which is a way of thinking about efficiency as it relates to the second law of thermodynamics. So first of all, what do we mean by a heat engine? A heat engine is a device that converts heat into work, or vice versa. We'll find out about the vice versa. It's a really important concept for assessing the efficiency of power plants, refrigeration cycles, and other systems that convert between heat and mechanical power. So let's look at a few examples. The train engine. The train engine converts heat to power. Those are mechanical power on the wheels. A power plant also converts heat to power, but in this case, we're taking mechanical power and use a generator to turn that into electricity, to push on electrical power. An air conditioner is also a heat engine, but it's one that does the conversion in the opposite way. In this case, we need power, and we use that power to generate heat. Now, in this case, what we're doing is we're taking heat out of a house and putting the heat outside. That's how the air conditioner works. It pulls heat out of the air in the house, pushes that heat outdoors. It's essentially concentrating the heat. The heat otherwise would be going the other direction. So in this case, we're using power to concentrate heat. All of these are heat engines, and the upper limit of efficiency for any heat engine is constrained by the second law of thermodynamics, which tends that systems tend toward less ordered states. So systems will tend towards disorder. And how close we can get to this theoretical best efficiency is what we call the second law efficiency. Now, if you want to see more about the second law and on entropy, which is the formal term for describing the disorder in systems, really suggest go to watch some other videos or do some reading to understand the second law of thermodynamics. We're not going to talk about that here. We're just going to presume we have a sort of understanding of that, or just breeze past it and just focus on the equations. So a power plant, as we mentioned, is a heat engine. It's a really important one for those of us who are working on energy and environmental systems, because fossil fuel power plants are what drives climate change. So we really need to know, it's one of the things that drives climate change, not the only one, but we really need to know how these things work. We've already talked about the first law efficiency, and that's shown here. So if we talk about the first law efficiency of a power plant, it simply relates the work that we get out divided by the flow of heat. In this case, it's coal coming in. So this is a power plant. And the first, and what we saw in an example previously was that a typical first law efficiency for a power plant like this might be 35%. So 35% of all the energy that's contained in coal eventually becomes electricity. The other 65% is waste heat. Waste heat that comes out the top or goes down into cooling water. So the question that we want to ask with the second law and with the sort of analysis of the power plant as a heat engine, we want to know just how good is it to be 35% efficient? What is that compared to? What's the theoretical best efficiency, and how close are we? Before we answer that question, we need to know something about the theoretical best. And the way that we do that is we consider the power plant as a heat engine. And this diagram shows the kind of classic diagram for thinking about heat engines. Instead of looking at a picture of a power plant, we're just going to look at this diagram. Now, it does map on to the power plant. In this case, the engine is the combination of the boiler and the steam turbine. And we're going to imagine that we've got one hot reservoir and one cold reservoir. So we've got a hot and a cold. Heat is flowing from the hot side to the cold side through the engine, and the engine does work based on that flow of heat. So that's our fundamental concept for the heat engine, is that temperature goes from hot to cold. We've got heat flowing QH QC, and that there's work coming out of the engine. Notice that the work is going to have to equal QH minus QC because of the first law of thermodynamics. We need to be able to draw an energy balance around that heat engine. So we know work is equal to QH minus QC. So that's how we can write this alternative form of the efficiency equation. We know that efficiency of the engine is the work divided by the heat that we put in. The heat that we put in this case, is the hot side work, or the hot side heat, QH. We can also reframe the net work of the system as QH minus QC because of the first law. All right, so this is just getting us set. So now we've got our heat engine idea. The source, remember, of QH is burning coal. The work that we get out of our power plant is electricity, but we can analyze it as a heat engine. We want to know something about the maximum work. That would tell us about the maximum efficiency of this heat engine. And it so turns out that the maximum work possible that comes out of a heat engine is related to the temperature difference between the hot and the cold side. And it's related this way. The maximum efficiency in this case is equal to this formula. So the maximum efficiency for any heat engine is equal to the temperature on the hot side, TH, minus the temperature on the cold side, divided by the temperature on the hot side. And we call this the Carnot efficiency. It looks like Carnot, but Carnot was the name of a person who wrote down and figured out this relationship for heat engines. And one thing that we can do is we can also kind of use algebra and rewrite this as 1 minus the temperature on the cold divided by the temperature on the hot. There's a really important note at the bottom here, is that these temperatures all have to be in absolute terms on the Kelvin or the Rankine scale. So remember that Kelvin degrees are equal to some number of degrees Celsius plus 273.15. So 0 degrees Celsius is the same as 273.15 Kelvin. And then there's another relationship for Rankine, which is for the absolute temperature that's related to Fahrenheit. So we always need to use absolute temperatures when we're making these assessments and figuring out what's the best possible efficiency. Or we sometimes call that the Carnot efficiency. That would be the best possible maximum efficiency for our power plant. So let's consider that coal-fired power plant. Some temperatures that might be at play might be 200 degrees Celsius, double boiling water, and 10 degrees Celsius, something like the atmospheric environment. We want to know what's the maximum efficiency here. So first of all, we need to convert this to Kelvin. So 200 degrees Celsius in Kelvin is going to be 473.15 Kelvin. And 10 degrees Celsius is going to be 10 plus 273.15, or 283.15 Kelvin. So we're going to compare the hot side to the cold side using this formula. Oh, and went one too far. So if we multiply, if we plug into our formula here, our maximum efficiency is equal to 1 minus the cold divided by the hot, and that's equal to 40%. So operating between a 200 degree and 10 degree reservoir gives us a maximum theoretical efficiency of 40%. We'll never get better than that. It's just not possible based on those two temperatures. Now, what can we notice here? One thing that we can notice is that the ratio of cold to hot is one of these kind of limiting factors. So the closer these two temperatures are together, in other words, the closer together the hot and the cold side, Tc divided by Th is going to be closer and closer to 1, which is going to push down our maximum efficiency. If cold and hot are really far apart, our efficiency can be better. And so let's see how that plays out. What if our temperature for the high temperature reservoirs increased and now it's 300 degrees? We still have the same cold reservoir. In this case, we have a higher possible efficiency. We can get an efficiency up to 50% if we have a hotter temperature on the hot side. So this would tend to make us want to build power plants that can be hotter and hotter on the inside of the boiler because we have a higher maximum efficiency, but then we become limited by our materials. Like maybe the steel that we're using gets brittle at that temperature. So there's always going to be some drawbacks, but this relationship shows us something about what we should want. We should want to have a bigger difference between the hot and the cold side if what we're doing is we're trying to extract work from our Carnot engine. So here is an example of a power plant, and we're drawing it a little bit differently. And I want to describe this diagram because it's one that you'll see a lot. We won't necessarily need to analyze all the different parts, but it's important to know a little bit about how these power plants work. This diagram shows how we can provide heat to the boiler. And in this case, we're providing heat at 600 degrees Celsius, which is the operating temperature of the boiler. What happens is that the boiler takes liquid water and it creates vapor at 600 degrees. That water vapor goes through a turbine, spinning the turbine to generate work. So it's like a big fan that the water vapor goes through. It comes out at lower pressure and lower temperature. So we've reduced the pressure and the temperature on the outlet. And we need to condense the vapor down to a liquid in order to put it through the pump and pump our liquid back into the boiler. And the power that generates that pump comes off the turbine as well. And so our condenser is operating at 20 degrees Celsius. So the operating temperatures of our boiler and our condenser define the temperatures for our heat engine, and we've got work coming off. Let's remember, what is our equation? What is our maximum efficiency that we could operate at? Remember, the maximum efficiency is equal to 1 minus the cold divided by the hot temperature. So that's when we work out using 600 degrees and 20 degrees, that maximum efficiency, it turns out that the maximum is 66%. And we can compare that to the typical efficiency of a power plant, which is 35. And that comparison is what we're going to call second law efficiency. So that has to do with how well we're doing compared to that theoretical maximum. And another way of writing this is that we say that the second law efficiency is the actual first law efficiency, so 35% in the case of our power plant, divided by the maximum or the Carnot efficiency for a heat engine operating at the same temperature range. In this case, it was 66%. So given 35% typical efficiency, actual operating efficiency, and 66% is the maximum, we would say that the second law efficiency of this power plant is 53%. In other words, it's operating at 53% of the best it could possibly do given the temperatures that are involved in the power plant.